Here. Will someone type in the chat if they can hear me? Can you hear me?
I think we can hear you.
Okay, thanks. I always get worried because I always forget to, I don't know how to work my microphone thing. So half the time I'll present for 10 minutes until I realize no one can hear me. Thank you. Okay, so just a quick little bit for this week. So just so everyone's clear, we are on week 3 for this course. Again, this is a pretty long semester, at least just because we run into Thanksgiving. So December 18th, I believe, is your last day. I just looked at that. So make sure you're staying on task there. So I got a lot of emails about the alternators amateur module, which I believe is the second or the third one. I have no idea why that one is acting funny. Most people were able to complete it. It just wouldn't show them their grade. So if that's the case, let me know. And if you send me an email, I can go in to Amatrol and see your attempt, and then I can manually enter your grade. If you don't have access to that module, make sure you have access to other modules. And if this is the only one that's like weird, we can figure something out so you don't not get any, or so you get points for it, basically. So just send me an email if you have questions on that. I think for those of you who have emailed me, I know a couple of you have, your grade should already be updated to reflect what you got in the amateur module. So, all right. So just a quick little bit here. Hopefully you can see my screen now. It should say week 3. Basically this week I think it's pretty easy, especially for the first section or segment of this week. So you have 2 quizzes for week 3. Towards the end, that's where it gets a little bit challenging. So I'm kind of going to skim through the beginning. And then what I ended up doing, because I think this might help, at least I'm hoping it does. So this last little bit I'm going to talk about here, this is a problem that the guy who does the YouTube videos, he did this for the impedance video for week 3. And I think it would help to walk through this again step by step slower. So, and then that way, if you have questions, you can ask them. But this is definitely it can be a challenging concept. There's a lot of math involved. So we're going to spend some time on this. Okay, so just a quick recap. Hopefully you guys all remember this from 120. So basically just resistance, what it is. So it's a measure of the opposition to current flow in an electrical current. And that idea is very, very important, especially when we're going to talk about reactance in a second and the relationship between resistance and reactance. But ultimately, so resistance we know is a component of our circuit as shown in this diagram here. And it's ultimately just impacting our current speed, right? And the intent of having like resistance or putting a resistor into a circuit is that you are essentially ensuring that the components inside your circuit are being protected, because obviously if we have too much flow running through our currents, it's going to negatively impact it, and it could be a safety issue as well. So just a quick reminder on resistance, because it's going to come up later in the slides. So now I'm going to talk a little bit about capacitance, which we talked about last week. I guess we talked about like what a capacitor is. So if you weren't there or have questions, let me know, send me an email. So there are 2 different terms here that might be kind of new to you, and that's the idea of capacitance and capacitive reactance. So these are not the same thing. So first off, that's very important. The best way to distinguish them is to look at the units. So capacitive reactance is measured in ohms, which what also is measured in ohms? Resistance. So basically what we're going to talk about at the beginning or at the end of these slides is that reactance and resistance do have a direct relationship with each other, and that's a prime like indicator right there, and it's the fact that they both use the same units. Capacitance, on the other hand, is measured in farads. So just take note of that. So essentially what capacitor reactance is, so it's the opposition to the change of voltage across an element. So I know that kind of sounds complicated, but if we go back to looking at this, you can see that resistance is a measure of the opposition to current flow as well. So basically the 2 terms are very much related there, and kind of in bold there. I'm not going to read it for you, but you can see I kind of put the best definition in the least amount of words between the difference between resistance and reactance. So just so you know, so they're not the same term, but they're both essentially used for the same purpose, and that is to essentially restrict the flow of current, or restrict the flow of current in our circuit for valid reasons, to, like we mentioned here, for like safety measures. The other little bit here to note on the back there, so capacitance, which we talked about last week, which the idea of a capacitor is to store energy. So capacitance is related to the ability of a circuit to collect and store energy. So it is inversely related to capacitive reactance. So for example, if you have more capacitance, you're going to be storing more energy, because that makes sense, right? Because we know capacitors store energy. So the bigger your capacitor is, the better it's going to be at storing energy. So you will have less capacitive reactance and less resistance. And it makes sense if you think about it, because if it's storing more energy and it's working better, right? It's storing energy. So we're going to have less capacitive resistance because we're going to have more energy being stored. So just like an example here, because this is kind of a quiz question too. So if you have 10 farads, that's going to have, which again, farads right there is telling you that they're talking about capacitance. So if you have 10 farads, it has less capacitive resistance than 5 farads. So just know that the greater farads you have, the smaller your capacitive reactance is going to be. Okay, so the next little bit of ideas here are this equation that kind of pops up. So the equation that is talked about a lot this week is this one right here that I have written. So it's XC equals 1 divided by 6.28 times C times F. So to kind of digest what that equation is doing, basically it's a relationship between frequency, capacitor, and capacitive reactance. So that XC there is indicating capacitive reactance. So for example, let's say, and I think in the problem on the quiz, there's a couple problems that might ask you to calculate capacitive reactance, and they're going to give you the frequency and the capacitor value, which is going to be in farads. So for example, just to kind of show the math here, let's say that we had a frequency of 5 hertz and a capacitor value of, gosh, I don't know, 10 farads. If we wanted to calculate the capacitive reactance, what we would do is do 1, I have my calculator here, I don't know this math on top of my head, 1 divided by 6.28 times 10, which is our capacitor value, times 5, which is our frequency value, and we would get 0.003. So that is telling you your capacitive reactance. The other thing I want to note, when you're doing these math problems, a lot of people get this problem wrong because they don't divide correctly, because sometimes it's difficult when you're dividing something and you have multiple things in your denominator, you have to use a parenthesis. So if it's easier for you when you're trying to calculate capacitive reactance, you might want to start with this bottom half. So first do the multiplication, so 6.28 times your frequency times your capacitor value, and then whatever number you get, do 1 divided by that number, and that'll be your answer. Just because, or if you have a graphing calculator, just make sure that you're putting the parentheses after you multiply, after basically here and here. So the parentheses have to show that you're dividing 1 by every component. Okay, so I kind of wanted to touch on this because this idea comes up a lot. Unfortunately, if you don't like Ohm's law, it's back. So Ohm's law, just a recap on that. So Ohm's law is I equals V over R, where I is your electric current, V is your voltage, R is your resistance. The other thing that is important for this week, and particularly when you're doing quiz number 4, the last couple of questions are related to this. So you'll see a problem like this. Actually, this is an exact problem on quiz 4. I just changed the numbers around a little bit. So let's say that you have a series circuit with an RMS voltage of 20 volts AC alternating current and two capacitors with reactances of 4 ohms and 1 ohms. What will be the total current in this circuit? Okay, so there's a couple things I want you to note here. One, it's a series, so that's important for this. Two, it says alternating current, not really important, but for future purposes, there's a reason that they're giving you that. Voltage, they give us that, and then they give us capacitors with reactances. And again, it's important to note that they said reactances, so that's why they're giving us ohms and ohms. So in this situation, we're not given a resistance in the typical way we are, right? We're not given with a resistor of 4 ohms and 1 ohm. So even though technically that Ohm's law equation isn't correct because we don't have any resistance, we only have reactances. Because reactances and resistances both use ohms, you can think about it in the same way and in the same equation. So the other thing I wanted to kind of bring up, because it's important as a quick recap. So we talked a lot about in ELT 120 that when you're calculating total resistance of series and parallel, it's different, and it's a different equation. So these are just the two equations to remember. So when you're calculating the total resistance or total reactance in this situation, if it's a series circuit, you can just sum them all together. When it's a parallel circuit, it's a little bit more difficult when there's only two values given. So basically, if you see ohms written twice, you can use this equation. But if you have 3 ohms, which I don't think a question on the quiz has one, it's a little bit more of a complicated equation, which you probably remember in ELT 120, it was that one that was like 1 over 1 divided by R1 plus 1 over R divided by R2, etc. That equation. But these are the two equations I would just remember for now. So back to this problem. So if you're trying to calculate the total current, you can use Ohm's law basically. So first you want to calculate the total resistance, right? So in this situation, since it is a series circuit, we can just add them all together. So 4 plus 1 is 5 ohms. Now that we know the total resistance or total reactance, we can simply do V divided by R to get I, which is current. So that is why I have 20 divided by 5 to get 4 amps. But again, just note that if this did say parallel, this would be a different answer because we'd have to use this equation. And I think there is a question on the quiz that has you do parallel. So just important to note. So this other idea I wanted to talk about, I showed this, I think the first or maybe last week, the sine wave and voltage and current, how they both function on a sine wave if you were to graph them in alternating current situations. So just a thing to note here that when you're using a capacitor, which again is a component of your circuit that's going to store energy or give you capacitance, your current sine wave will have a 90-degree phase shift ahead of the voltage sine wave. So to kind of break that up, what that's meaning is, if you can look at this graph, I think it's best to visualize it. That current graph, if you can see, it's a little, that's the red line. It's a little bit ahead of the voltage graph. And you can see they're still kind of going on the same like pathway, right? They're still going in the same amount. It's just different how, like, it's just ahead of it by 90 degrees. So basically that's just a mathematical component of this. And the reason for that is due to the fact that voltage and the integral of current are related, but I think it's like a intense mathematical like concept. So I don't really want to go too in deep in that, but just note that that is the case that when you graph them. And it kind of makes sense if you think about it, because these, I don't know if in trigonometry yet you've talked about the unit circle, but if you haven't, these numbers here will become familiar. And if you have already talked about the unit circle and the math components, these numbers should already be familiar. And it's related to those numbers, pi over 2, pi, 3 pi over 2, 2 pi are all numbers on the unit circle. And that's where the unit circle is so valuable. And it's because when we're using trigonometry, which is very much using cosine and sine, those values are values on the unit circle, and they're values on the unit circle because when we're graphing sine waves, those are the major pieces where we can see shifts and changes in our graph. Okay, that was a mouthful, but really just note here that there's a 90-degree phase shift, which again is just taking that sine wave and kind of shifting it over. Okay, So the next very important concept that we talk about, and that's a major component of the quiz 5, is this idea of impedance. So impedance, and I love this diagram, not because one, it's got mathematical like reasons that this actually is helpful, but also I think it helps show what impedance is. So essentially impedance is just the opposition of flow due to reactance and resistance. So if you've been following along for the past 18 minutes, this should really kind of tie everything together. And how I mentioned at the beginning here that this is what resistance is, the opposition to current flow in an electrical circuit. This is what capacitive reactance is. This is the relationship between them. And we know that both of them are still having a, gosh, sorry, I lost myself for a minute, but we basically know the relationship between both of them. And the fact is that the sum of both of those, or like when we're collectively talking about reactance and resistance, that is the term for impedance. And it makes sense to put it on a triangle like this if you think about it, because impedance is that longer line there and reactance and resistance are that shorter lines. And it makes sense because impedance is, you know, calculating both of them. So it's kind of connecting both of them, as you can see. Okay, so something that I think at least I thought was confusing the first time I watched it, just because it definitely has a lot of math in it. So again, I just wanted to touch on this last video in week 3. So this is an impedance video, and I just kind of want to run through this. So in the videos towards the end of this week, they talk a lot about math and triangles and trigonometry. And this is a huge component of this week. And so I think it's important to run through this problem. So basically, at the beginning of the video, Eddie talks about these two equations, which are listed here in the right corner here. And those equations should look familiar, because if in school, we talked a lot about Pythagorean theory, and that's exactly what that is right there. So that is just Pythagorean theory. So we know that's a squared plus b squared plus c squared, or you know what it is, I'm hoping. But if you don't, let me know and I will show you that too. But these equations, anytime you see these equations, it's always related to a triangle. So that's, I guess, the first thing to know here. So that's why in this equation, he's drawing triangles. And if that idea isn't making sense to you, just note that it's ultimately coming down to this and the fact that impedance is related to reactance and resistance. So on this right here, something that I think is very, very important before we even get started on this problem, and it's the fact that make sure that you know the acronyms for all of those different terms, because they are in this equation here, which we'll use that equation a lot. So just note that voltage is denoted by V. This little t that's below it, the subscript t, just means total voltage. Z is referring to impedance, which is again that Z with the T is just saying total impedance, and we know that that's in ohms. X is referring to, so XC there, X with the little c is referring to capacitive reactance, which we know is measured in ohms. R is resistance, which we know is measured in ohms. I is current, which we know is measured in amps. If you look back up these equations, all they're saying is that impedance, so the total impedance is equal to the square root of the capacitance reactance squared plus the resistance squared. So that's all it's saying. But I know it's a little bit confusing, but that's why we're drawing triangles, and that's why I wanted to explain it more. So these are kind of the steps that Eddie outlines in this problem. So in this situation, or this problem, the intent was, and I think he doesn't really state it, but basically the question says, what is the total current and what is the voltage drops? And this is what you're given. So this really should be bolded and should be at the beginning, but that's what the problem is asking you to do. And that's a problem that is very similar to one you might see in the quiz. So again, I'm looking for the total current and the voltage drops. So if we look on this diagram here in the middle, what that's showing us is a circuit, and it's showing us that we have 20 volts as the total volts, right? Because that's where the battery is. It's showing us we have a resistor of 3 ohms, because that's what those zigzag lines are. And then it's showing us this new one. So this is also measured in ohms, but we don't have the zigzag. We have 2 parallel lines. So what those are indicating there is that we have capacitance. So, and we know that because Well, the reason I guess I would think about it is because you know that capacitive reactance and resistors or resistance can be in your circuit. So that's just kind of a new term that might is good to know, and a new symbol, I guess, that parallel line is good to know too. Sometimes it might be confusing because sometimes I would draw like parallel lines like that in ELT 120 when I was doing a to know a battery, but just note that since it says ohms there, you can right away, and since it's a parallel line, just right away know that's reactance. Okay, so now that we kind of talked about that diagram for a minute, so step one, Eddie says in the videos, is to draw a triangle. So what he means by that is basically to draw a triangle to symbolize these equations, because these equations are the ones you're using, and anytime you're using these equations, you're dealing with Pythagorean theory, which is using right triangles and all of that. So that's kind of what this triangle is showing you. So what it's showing you here is that you have 3 ohms on one leg of the triangle, 4 ohms on one leg of the triangle, and then you have this long one. If you go back to this, it should hopefully make sense. And it's the fact that the small one leg is reactance, one leg is resistance, and the longer one is impedance because they're related to each other, and impedance is, using both components. If you look back at this, we see that 3 ohms is right here, which is our resistor. So it would be this one. 4 ohms is our capacitive reactance, which if we go back to this is this line. And then this long line here, right, is our impedance. And in order to calculate the impedance, we can simply use this equation here, right? Because we're given our resistance of 4, and we're given our reactance, capacitive reactance here of 3. So simply put, the impedance is just 3 squared plus 4 squared and the square root of that, which 3 squared is 9, 4 squared is 16, 9 plus 16 is 25. So that is why the square root of 25 is written here. So square root of 25 is just 5. So that's how we know that the leg of the triangle here is 5 ohms. And we also know that that is ZT, or our impedance. So that's the first half of this equation, and that is that we calculated impedance. So now that we calculated impedance, we can easily calculate total current. And that is because in step 2, Eddie says that to find total current, we can just do the total voltage divided by impedance. We already found impedance in step 1. So it's that is what step 2 here is showing here. And what he's doing is doing our Z, which is our impedance, which we know is 5, our voltage, we know it's 20 volts because of this initial problem. 20 divided by 5 is 4 amps. So right away there we have our current. And then the last step here, so in order to find voltage drops, 2 new equations kind of pop up, and that is I times X and I times R. So I again is current, which we just calculated as 4, and R and X, we already knew those values, right? So we knew that X, which is our capacitive reactance right here, is given as 4. So that's why 4 times 4 here is giving us 16 volts as our voltage drop. And that is why 3 times 4 here, I times R, is giving us 12 volts. So hopefully that made sense and that helped. But essentially this idea is really, really important for this week. And also note that in some situations you might be given the total current, but you might have to use this equation to find the total voltage. So sometimes you might use different equations. Sometimes this leg or how you draw your triangle might change, which I think if you have troubles on that, send me an email and I can explain them, or I would look back at that impedance video. But essentially this is the main idea. So just using these 2 equations, and the way to use these 2 equations is to draw these triangles and just note what everything in this equation means. This is the most important piece. So really this was all I had. So I guess if there's any questions, I think we have time for that. So hopefully this helped for those of you that were on. I will also put this on, I'll send the link to everyone, and then yeah, so just send me emails if you have any questions related to this concept or any of the concepts that I talked about, and then I'd be happy to help. So thank you. And if you want me to do re-explain something or stop and go back, just let me know. So we have a half hour. But if not, you're free to go and just send me an email if you have any questions for this week.
So I have a question because I just got on here because I lost track of time because I was actually doing homework. This is a test question, actually. I just did one of my quizzes and I got one question wrong. And for the life of me, I don't know the formula. I thought I did it right, but I got it wrong.
What question was it?
So it's number 6, and it says, I think this is what you're going over right now anyways. A series circuit with 100 volt has a resistor with 300 ohms and a capacitor with 400 ohms. What will be the voltage drop at the capacitor? So I thought I was supposed to do like
this. So does it give you current?
no, I just have voltage and ohms.
Perfect. Okay, yep, this is exactly what the problem is. So just to kind of run through it again. So in that situation there, you are given your total voltage and you are given your ohms, and the ohm values there, they should have one. Does it say if one is a reactance or a resistor, or does it just give you the ohm?
Yeah, there's the resistor's 300 ohms and the capacitor's 400 ohms, but it wants the voltage drop on the capacitor.
Okay, sorry. I don't have the problem pulled up, so that's why I can't. Okay. I thought I might have to ask you a couple times. Basically, this is exactly the steps you'd follow there. So first, you're going to want to draw. First, note this equation. So this equation is the one that we have to find, because in order to find the voltage drops, you have to first calculate the current, because the current here is directly related to voltage drops. So in order to calculate voltage drops, you do the current multiplied by X and R, which are our capacitive reactance and our resistance, but we don't know current, right? Because it doesn't give you in the problem. So that is why we have to, that's the equation and that's what we have to solve. That's the bulk of the problem. So first you're going to want to draw a triangle. So in that situation here, you're going to want to draw a triangle like this, where you have your reactance on one leg, your resistor on the other leg, and then basically use this equation. So
I forget the values. Screen. Are you sharing?
Oh, you want me to? Yep. You know what? That would.
Oh, I didn't know if you were drawing something.
Nope. Okay. That is it back.
Okay.
Sorry, I didn't realize I.
No, that's okay.
Okay. So back to that. Here is just the values for everything, what everything equals. Here are the two equations that are most relevant. So in order to calculate voltage drops, first we need to calculate current. That's the main bulk of this equation. So this is the main equation we're going to be using. And that is because everything basically is kind of like a chain. In order to calculate one thing, you have to calculate 5 other things before that. So since we are given the reactance and the resistor, first you would draw your triangle here. And you would put the resistance on one leg, the reactor on the other. Use this equation here. So it would be the square root of the resistor squared plus the reactance squared. Type that into your calculator. That is going to spit out a number. That number is going to be your impedance, or ZT. And the reason that we want to calculate impedance is because impedance is used to calculate current, and current is used to calculate voltage drops. So that gives us back to part 2 here, that we know the voltage. It gives you that in the problem. And we know the impedance because we just solved that, or Z, right? So voltage divided by Z is going to give you I. Once you have I, or the current, you can calculate the current drops, or the voltage drops.
Okay, so I did 300 squared plus 400 squared, which is 250,000 or something like that. And then I did the square root of 250,000, which is 500. And then, so I'm supposed to do 100 divided by 500.
You said that give me your reactance and resistor values again.
The resistor's 300, the capacitor's 500.
Okay. And just gonna double check the math there. Sorry.
And the voltage was 100.
So 300, 500, I got 583 as my impedance. Is that what you got?
Oh no, I got 500. What am I doing wrong? This is like the only question I miss. I don't know why that's what I'm.
Okay,
struggling with.
so.
I think she said it was 300 and 400.
Oh, she's
Yeah.
400. Okay, yep, then you were totally right. This is me not being able to listen. Yep, 500. You're right. Okay. So you would do 100 divided by 500.
Okay,
Get
and that
0.2.
gives me 0.2.
Yes, and then
But my answer or the options are 80 volts, 60 volts, 20 volts, and 100 volts. So do I need
yes,
do I
and
do
that
it
makes
that
sense
point?
because now we have to do that last step,
Oh, okay.
which is I times X and I times R. So 0.2 times our X, which you just told me 3 and 400.
Oh, okay.
0.2 times 400. So 0.2 times 300 is 60 and 0.2 times 400 is 80.
Oh, well, there we go. That's the step I. All right. I don't know why that was so confusing for me. I just didn't know the formula I was just reusing.
No,
that's
that's a confusing problem. That's why I had a slide on it because it definitely. But I'm glad you had that question because now everyone else on this, hopefully, that question will be easy. So
yeah,
yeah.
I hope so. Hopefully that helped other people. I appreciate that.
Yeah, of course. Any other questions?
I don't like this math. This math is way worse than circuit analysis one. That's just too many formulas to remember.
To be honest, like I was terrified to teach this course solely because, and I am so glad I don't have to teach the math portion because I would be awful at it because I'm not great at understanding trigonometry myself, so I definitely should not be teaching it. So I'm glad that I teach the electricity side of this course because at least
the math part of it's fine. It's just knowing what formula to use. That's the part that's hard for me because there's so many of them.
Definitely.
And I have them written down in my notes, and I have the presentations and the slides, and I'm like trying to find it.
I think the best thing there is I would write down the trend of how you use the equations because I think that's what gets people is they're trying to find voltage drop and then there's not an equation that's specifically for voltage drop, and that's because we have to use this equation to find impedance, and we have to use this equation to find total current, and then we use this equation to find total voltage drop. So I think it might help if you're writing the equations to maybe write like the chain of equations of how you might get from one place to another. So maybe in your notes, put voltage drops and put all three of these equations with like an arrow going to them. So you know, like, okay, to find voltage drops, I use this equation, then this equation, then this equation. That's my best advice for you. But
okay.
if that helps. But it's definitely a challenge. So I feel for you. Hopefully this helps. And like I said, send me an email if there's a problem that's confusing. I'd be more than happy to help send that back to you.
Awesome. Thank you so much.
Yeah, of course. I'm going to stop sharing. And then if any of you still on have any other questions. Hello?